We are going to discuss non-conventional machining process, that is laser beam machining. In short, it is also called as LBM process, and we are also introducing the micro machining process. First, we will discuss about the laser. What is the laser? Laser is light amplification by simulated emission of radiation. It is coherent, that is all photons are in one phase. It is highly collimated, means parallel beam is produced, and it is a monochromatic source, means what? One color and one wavelength. There are generally two main categories. One is solid state lasers and gas laser. The various modes of operations for this laser are continuous mode for cutting straight paths and pulse mode for thin cutting. Next, we will discuss about the principle of LBM. It states that if an atom or molecule of the lasing material is raised to higher energy level E2 by an outside source like light, heat or chemical reaction, it does not permanently remain at that state. Sooner or later, it decays back to its stable lower energy level, that is E1, releasing a photon of light. The frequency of emitted light depends upon the difference in energy level E2 minus E1 and the Planck's constant. If the photon of light so released comes into the contact with the another atom that has been similarly raised to be higher energy level, the second atom is triggered to return to its stable energy level E1, releasing another photon of light. The two photons so generated are identical in wavelength, phase, direction and energy. This sequence of triggering is multiply manifold to produce this laser beam. Next, we will discuss about the construction details of this laser beam machining. The figure shows the setup for this laser beam machining, which consists of a simultaneous stimulating light source, that is xenon flash lamp, and a laser rod. Laser rod or laser tube consists of a pair of mirrors which are placed at each end of a tube. Setup also consists of a flash tube or lamp, laser, power source, focusing source, and cooling system. The whole setup is fitted inside an enclosure which has highly reflective surface inside it. The laser used in this process may be solid, liquid, or gaseous type. The solid type carries reflective coating at their ends, and gaseous type produces continuous laser beam and is suitable for welding and cutting operation. Next, we will discuss about the working of this laser beam machining. In that case, first place the workpiece on the table. As there is absence of cutting force, fewer work holding devices are needed. The focal point of the laser is intentionally focused onto the surface of the workpiece for providing the heat in a concentric manner. Due to the striking of laser beam, heat is generated at the workpiece surface, and as a result the material vaporizes instantly, producing curve in the material. The movement of machine axis is through the computer control, which helps to achieve the required profile of the workpiece. Heat affected zone is minimum in laser as compared to the flame cutting. To clean the molten metal that has not yet vaporized or clogged on the surface of the workpiece, the assist gas, that is inert gas or exothermic gas, is used for this purpose. Under pressure is passed on to the workpiece. Next, we'll discuss about the advantages of this laser beam machining process. It has an ability to cut almost all materials. No limit to cutting path, as a laser point can move in any path. No cutting lubricants are required, as there is an absence of direct contact between the tool and workpiece. Thus no forces are induced, and as a result it is not necessary to provide the work holding system to hold the workpiece. The fragile materials are easy to cut on a laser without any support. Flexibility exists in precision cutting of simple or complex part. There is no tooling cost or associated wear cost due to it. Next, we will discuss about the disadvantages of this LBM process. Laser processes involve high capital investment in and high operation cost. It laser holes are tapered to some extent, approximately 1% of the drill depth. It can't drill blind hole to precise depth. Heat affected through the lasers may change the mechanical properties of the metallic material and alloys. The processing time in larger hole is slower due to trepanning action involved in it. Next, we'll discuss about the application of laser beam machining. Beam machining is used for making very accurate size holes as small as 5 microns in metal, ceramic, and composite. It is used for trimming of sheet metal, carbon resistor, plastic parts. It is used for cutting complicated profiles on thin film for making ICs, for dynamic balancing of precise rotating components like watches. One of the problems associated with the conventional approach in cutting of tough material such as titanium alloys is that at high cutting speed the life of cutting tool is very short. As the titanium alloys are used extensively in the aerospace industry, there is a tremendous interest and curiosity for developing this technique, especially for enabling higher cutting rates. In drilling, it is used in drilling of micro-size holes in difficult to machine refractory material is the biggest area of the laser application. It is also used in cutting holes and slots larger than 1.25 mm. It is also used for marking, and it is achieved by producing a series of overlapping blind holes that produce a uniform smooth bottom groove. Next one is cladding. It is done in the application where only a portion of work piece area needs to be protected from wear or corrosion without requiring the whole part to be made of high cost material. This laser beam machining is also used for heat treatment. Now we will discuss about the micro machining. We just cover the introductory part of this micro machining. Micro machining is a process in which the dimension of the components machined are of the order of microns. The techniques of this micro machining. There are two types. First one is lithography based micro machining technique, and second one is non-lithography based techniques. In lithography based techniques, again there are three types. First one is bulk micro machining. The structures are carried out of a substrate by chemical or physical etching method. Second one is surface micro machining. Thin layer up to 3 to 4 micron thick of material are sequentially deposited and etched to create multi-layer stack of desired geometry. And third one is micromolding. This process involves making a micromold which is then used to create microstructure of different materials like metal, ceramic, plastic, and semiconductors. Now we'll discuss about the lithography based micromachining techniques. These are various steps involved in this technique. First one is cleaning and preparation. In this step, the wafers are chemically cleaned to remove particle matter on the surface as well as any traces of the organic, ionic, or metallic impurities. The desired rectangle pattern is also generated using photography technique. Second one is photoresist application. Photoresist layer of 0.5 to 2.5 micron thickness are obtained by applying the PR to substrate in liquid form and then spinning at several thousand rpm for 30 to 60 seconds to get a uniform coverage of the surface. Next process is pre-baking. In this, the it is also called as soft vaping of the wafer to remove the solvent from the PR and harden it. This step is carried out on a hot plate that has been heated to around 100 degrees Celsius. Next one is registration. This is important step in photolithography process and is mask alignment. The mask is aligned with the wafer so that the pattern on the mask can be transferred onto the wafer surface. Each mask after the first one must be properly aligned to the previous pattern. Next one is UV exposure. Once the mask has been accurately aligned with the pattern on the surface of wafer surface, the photoresist is exposed through the pattern on the mask with a high intensity ultraviolet light. Next one is the development. The behavior of resist film on exposure and development depends upon the exposure energy and whether the resist is positive or negative. As the exposure is increased above threshold energy, more of the resist film remains after the development such that at 2 to 3 times threshold energy level where little of the resist film is dissolved. For positive resist, the resist solubility to its developer is finite even at zero exposure energy. The solubility gradually increases until at the threshold the resist is completely soluble. Next step is hard baking. After the exposure and development sequence, the wafer is hot baked to harden the remaining photoresistant and improve adhesion of the photoresist to the wafer surface. In addition, a deep UV treatment further strengthens the resist against high energy implants and dry etches. Next step is etching. Modern ICs are processed exclusively using dry etching, which involves the use of chemical reactants in low pressure system. In contrast to the wet etching process, dry etching allows for a high degree of directionality, resulting in higher anisotropic etch profiles. Also, the dry process requires only small amount of reactant gases. Last one is the photoresist removal. In this process, it is to strip the photoresist that remains. One way of doing is to expose the vapor to oxygen plasma. And in case of non-lithography based techniques, they are the techniques used for limited production, such as for exploratory purposes in academic and industrial research laboratory. This is the for micro machining. Thank you.